In this video, we are going to learn about properties of logarithmic functions that are very useful when solving exponential and logarithmic equations and also when simplifying certain algebraic expressions. So we're going to talk about 5 properties along with their proofs, and you can skip those proofs using the timestamps given in the description. And also at the end, we can talk about summaries of the results and also some errors that we make sometimes. So let's start with the relation between the exponential function and the logarithmic functions, and we know that when x equal ay, a is the base, we can write this as a logarithm. So we normally write, if x equal ay, we write this one as log to the base a of the number x equal y. So we remember that y is the exponent, so the log is the exponent in this case, and the assumption is we assume that a is positive and also a not equal to 1. So that is the major relation between the exponential function and the logarithmic functions, and using this we can have several interesting properties. So let's start with the property number 1. So property 1. So as the first property, we have log of to any base 1 equals 0. So this is a very important result when you simplify certain algebraic expressions. And also we have the log to any base a of a. So that means log base a of a, which is equals to 1. So these are two important results. And then let's see how we can prove these two results. So this is very easy, easy to prove using the definition. So so we know that so let's talk about the proof. So we know that 1 is a to the 0. We know that a is not equal to 0, so we can write it like that. So that means if you write this in the log form, this means that log to the base a 1 has to be 0 because that's the index. So that's very simple. That's the first one. And also you can see the other follows from. So other follows from the fact that you can write a as a to the 1. So that means if you write a using the base a, the index that you get or the log is 1. So that is how you prove the second one. And then these have two major results when a equals the natural base e. So that means you can write in particular. So we have. So in particular we have ln1. That means when a equal e, ln1 is 0, and we also have ln e equals 1. So these are very useful again when solving problems. So you may remember these two results. ln1 equals 0 and ln e equals 1. Okay, so let's go to the second property. So with the second property, we have these two. So this is the property number 2. So let's say again for a positive and not equals to 1. So we can have these two results. So the first one is a into the log. So this has a power ax equal x. So that means if you raise a to the power log a x, you get x back. So this is true for any x which is positive, because you can see that x has to be in the domain of natural log. And the second result, which is log to any base a to the ax. So this is equals to x, but in this case ax is any real number. So for any real x. These two are also very important, and also in particular we have these very particular important results. So in particular we have if the base a equal e, log a become natural log. So that means you can write the first one, you can write as e ln x equal x. This is very useful when simplifying certain expressions, and also a lot of proofs in calculus. And also the second one becomes ln e x equal x. So the second one is valid for so the first one is valid for any x positive. The second one is valid for any x in R or any real x. So again, these two are the two results, so also very useful in solving certain problems. Very, very useful. So E ln x equal x and ln ex equal x. You can see the switch the order, E ln and ln e. So you can see one as an exponent, the other one is a function. Good. So let's try to prove the first two results, because the second one is directly follows from when a equals. So this happens when a equals e. So good. So let's try to prove this. So we can see that to prove the first one. So the proof, we can say since log a to the x equal log ax. So this is the same thing, log ax equal log ax. Now what you can see, you can actually consider one of the log x. So this as one value, okay, just a value. So if this is a value, what we can do is you can write the exponential form. So if you write the exponential form using a as the base, so you can directly get the result. So that means just by the definition, so just by the definition of the log, what you can do if you write this as base, so it's a to the power log ax has to be x. So this is just by the definition of the logarithm, because you're going to consider a as the base and then the log is just a number. So that means if you raise to that number, you should get x back. So it's just very simple. So this is not how we normally prove in books, but you can see it's a very short proof. And also the other one also you can prove it like this. So similarly, it's a very short proof. Similarly, since we have ax equal ax, so again just by the definition you consider one of the a's as the base. So if you consider a as the base, and then what you can do, you write the log form. Now if you write the log form, what's the log form? If you write the a, so that means a log log base a to the number x has to be x, just by the definition of log. So in this one you consider a as the base, and you consider this one just as a number. Okay, so just one, this one, so that's the number you are talking about, and that is the base you are talking about. And the same thing in earlier. So so that's the base you are talking about, and this is the number you are talking about. So that's the number. So you consider this as a number. Okay, so that's a proof, very short proof. And then what we have is let's look at like a few examples and how to use these in solving problems. So let's say first one is simplify the first one to, let's say, log base 2x. So you can see this is directly coming from the first result. So we have in this case a equal 2. So if you put a equal 2, this will be simply equal to x by property number 1. Okay, by property number 1. And then so 2. So let's look at the next one. Let's say we have a log a half base, that's the base, and half to the let's say some number like negative square root 3. So this is directly coming from the second result. So what the second result says, log base a to the ax equal x. So that means this has to be simply negative square root 3, directly coming from the part 2 of the property. And then we have c. We have natural log e to the kt. So this is a very common problem. You can see these kind of problems in like physics, chemistry, biology, and all of those classes, you're going to see these kind of expressions. And we talk about that this looks like a e ln ln e get cancelled out. That means this is like kt. So that is the result. Is again coming from the part 2 of the result. So it's a direct simplification. And then d. So how about e to the negative ln let's say x cube? You're gonna get things like that when you try to take differential equation classes. So this is one of the common thing happen. So let's just try to do some basic simplifications. So what we can do, you're gonna see that the negative index. So just to remove the negative index, we're gonna bring it down. So if you write it down, you can write this one as e ln x cube. Now you can see this is the property number 1. From the property number 1, you can see that it looks like this get cancelled. That's how we kind of remember. So that means this is simply 1 over x cube. That means if you bring it up, this is going to be x to the negative 3. So that is how you're going to simplify. But there's a result later in another property. When you talk about a property number 3, you're going to see that there's another result that you can directly use for these kind of problems. But this is how you can do it using just the property number 2. So good. And then e. So we have, how about this one? So let's say base 10 log. You know that when you write base 10, we normally don't write base. So it's a log x. That means if you use the property number 1, you can see this is simply x, because here the base is 10. So these are some of the simplifications that you can do using just the property number 2. So let's look at now the property number 3. So property number 3. So this is one of the very important result for logarithmic applications. So for example, so let's say for a positive and not equal to 1, and let's say you have two numbers a and b which are positive, because we know that for the domain uh, uh, those two numbers you're gonna should be positive for logarithm. Okay, so let's say the first result. So the first result is log for any base a, the product. When you have product, we normally put a parenthesis to mean that you take the log of both, because if you do not write the parenthesis, what will happen, you take the log of the first one and then you just multiply by b. So that is not what we mean. So you have to put a parenthesis here. Equal, what it says that the log of a product is equal to the um, sum of the each log. So that means this simply equals to the sum. So it's going to be log a to the a plus log a to the b. So it's a very interesting result. So you can see that what happens if there's a product, it becomes a sum. The reason is log is the index. So the easiest way to remember this result is think like something like this. Let's say you have 2 to the 3 times 2 to the 4. You can see that this is simply 2. You add the powers. So it's a 3 plus 4. That's exactly what this result means. I mean, if you multiply two numbers, so what will happen, the new index becomes simply the sum of the previous index. So that's the log form of these results. That's how you remember, it's a sum, you add them. And then similarly we have the division. So we have log a divided by b. In this case actually you don't need the parenthesis because it's a division. So this is log a to the a minus log a to the b. And this also very easy to remember using the exponents. We know that if we have 2 to the 3 divided by 2 to the 4, the exponential form is, it is 2 to the 3 minus 4. So you subtract them. So that is why you're going to subtract the index, because log is the index, the powers. Okay, and then the third result, so we have log a to the ar. So you have some power r. So if there's a power r, what will happen, we're going to take that r out. So this is simply going to be r times log a. So this is very, very useful result. So we remember this normally as the power out formula, because it looks like you're going to take the power out. So the power term out. So I'm going to call this as power out formula. So power out formula. So remember this as a power out formula, because if there's a power, you can just take it out. Okay, so and then there's a special simplification going on because of the third result. So in particular, a to the x. So if you have a to the x, you can simply rewrite this one using e x l n a. So that is the result I was talking about earlier. So this is like a very useful result when you simplify certain algebraic expressions. So we have a base a and you use e. That's why you have ln a. So you can see this is simply you can write this one as also e ln ax. So what happen is you write this x term in front. So that is why we have this result, because we know that the ELN normally get cancelled. That's what one of the results that we had earlier under property 2. So you can see it is simply coming from there. So what we normally do is you write x in front. So that means ax equal e x ln a. So that is another very useful result, and this is also true for any x. So for any x. It's true for any x. So this is very, very useful result. So this is property number 3. So let's try to prove these results. So let's go with the first one. It's very easy to prove because we just write. So the goal is to we try to bring it to the power form, the index form, and then we know that when you multiply, you add index. So try to use the result here, just the basic algebra result. So let's see how we can use that then. So to prove these results, what we're going to do, we're going to write a and b using the base a. So that you can do because since a and b are positive numbers. So we're going to say let a equal a to the x. So a you can write as a some power of a. And also you can write b the same way. So you can say b also equals to some power of a. So the reason is you can see if you remember the graph of those functions. So so those two graphs have, depending on whether a is positive or negative, those two graphs gonna be like that, either like this or like that. So that means at some point this has to match to a. So that's a, and then that is the x you are talking about. And at some point b, we don't know where the b is. Let's say b is here. So at some point b, so that's the b, and you can see there is a value y. So that is the x and y value, depending on whether a is positive or negative, we don't know, but at some point it should gonna give you the x and y values, because the range is all. So you know that the range of these two functions is 0 to infinity. So that means you can always, there's a value x and y. So that's a valid argument. So now what we're gonna do, so then what we can do, we can write the product. So let's say then so the product AB, then the product AB simply equals to a to the x times, because b means a to the y, so that means from the algebra this is simply a to the x plus y, because we know that from algebra when you multiply two numbers with the same base, what we can do, we can add the two index. So that's what we do. So that means we use that just basic algebra result. Now what we can do, we write this exponential equation using the logarithmic version. So what's the logarithmic version? This means that the log of a base a to the number ab is simply equals to the index. That means in this case x plus y. This is just the definition of the logarithm. So we just use the definition of the logarithm. Now what we can do, we know that what is x. So because x equal because x a equal ax, so that means x is simply natural, is a log a to the a. And what is y? So if you look at the second one, y means simply log a to the b. So just coming from the definition. So we can just get the exponential version, you write as a log version. So that is the proof of the first one. It's very simple proof. And then Now to see the second one, to see the second one, so what we can do, we can write earlier like a over b, which is a to the x over a to the y, and then this is a to the x minus y. Now we write this equation in the log form. So if you write this in the log form, this is simply means that log a to the a over b equal the exponent. Exponent means x minus y. That's just the definition of the log. So that means, as before, x is simply log a to the a minus log a to the b. So that is the proof of the second. It's a very simple proof, very simple proof. And then we can see how we can get the third one. So for the third one, we can have a similar argument. So for the third one, so for number 3, what we can do is, let's write log a to the ar, a to the ar. So now what we can do is, we can replace a. So what is a? So we know that the log a to the a means a to the x. That's how we pick x. That's a to the x. And then to the r, now we're going to simplify this part. So when you have power of a power, we know that you multiply the two powers. That means this, you can write this one as simply log a to the, you multiply the two powers. So when you multiply the two powers, this simply becomes x times r. Now we can use the property number 2, because in the property number 2, we know that when you have log a to the a, that means this simply going to be the power, like the number up there. So that means this simply going to be xr. This is simply coming from the property number 2. This is coming from the property number 2 we discussed earlier. So that means is x and r, but x is simply, again, we know that x is, so we can write r in front. X means log a, that is x. So that is how you're going to prove the third result. And also this also can be this is simply a not. So what happens if a is an positive integer? So if, let's say, if r is a positive integer, we have a shortcut, like different proof. Positive integer, if r is a positive integer, then we can write a log a to the ar as log, we can write the expanded version. A to the r means you multiply a r times. So it is a times, like that. There are r times. Okay. So this is r times. R times. So now we can do, this is just the product rule. So since this is the product rule, from the multiplication rule, this is simply going to be, you have r many sums. So it's going to be log a to the a plus you have r many terms from the product rule, because the product become a sum. So that means there are r many terms here. So there are r many terms. Earlier is r times, now r terms. Earlier it is r times. So what does that mean? That means r times, so there are r many, so it's going to be r times log a. So but this is only true for positive integers, but this can help you to remember the result. But what we have is, can be for any r, any r. So this also, as we talked about earlier, we remember this as what we normally call the power out formula. Power out formula. Reason, it looks like you're going to take the power out. So R coming out. So it's going to comes out. So that's why we call it the power out formula. Okay, and then in addition, so we can have these two results. So we can have, let's say, in addition, so we can say, since E ln x equal x, that's one of the results that we talked about earlier in property number 2. We can write like this. So since this is the case, we can write this one as ax. So you can simply write, so what we can do, we can replace this x by ax. If you replace this x by ax, we have ax equal e ln ax. Now what we can do, we can take this power out and write this in front. So if you write this power in front, that's a power out formula. So you can write this one as e x ln a. So that's how you get the other result. So it's very simple argument. So it's just using the power out formula, you use property number 2 and property number 2 earlier, and the part 3 of this. Good. And also I'm going to show you like another method to show this result, because this is like a very important result later. So I'm going to show you this another trick. So I'm going to say method 2. So it's good to remember like certain algebra tricks, because it's very useful. So we can write this one as e ln ax. So and then what we can do is we can take the power out. So we're going to bring this in front. So we can write this one as e x ln a. Now what we can do, you can see this is just a product. Since this is just a product, you can switch it. So you can write this one as e ln a times x. Okay, just a product, like 2 times 3 equal 3 times 2, something like that. 2 times 3 equal 3 times 2, the canonical. Now what we can do, remember when you have a power of a power, like for example, if you have a x to the y, what we normally do is we're going to multiply the two powers. We can write this one as axy. We're going to use that. So we're going to go backward now. That means if you have a product, you can write this as a power of a power. That means we can write this exactly like e to the, you can say ln a, the whole thing x. So it's like a power of a power situation, because you have the two powers, it's a product, but product you can write as a power of a power. But now you can see that this is simply a, because this is the property number 2. This is just a, because eln get cancelled. This is just a, so it becomes ax. So this is simply equal to ax. So that is the other method to prove this result. So these are all proofs. Okay, so you can so let's look at some of the examples that you can do using these results. So let's write example, first example. So let's say write, these are the real problems, write as a single expression, single, or what we normally call the condensed form, condensed, right, as a single, or the condensed form, single logarithm. So let's look at the first one. Let's say we have, so I'm going to write a few examples and let's do one by one. So the first, so I'm going to write a few of them. So let's try these problems. The first one is A, which is log A 7 plus 3 log A 2. B, 2/3 log 8 minus log ln 12. The second is ln. That means a natural log. And the third one, 3 log x plus 1/2 log x plus 1. In this case, it's a log 10, or the common logarithm. This is the base 10. And then the d is 3 ln s plus 2 ln t minus 1/2 ln t square minus 1. So let's do one by one. So so we can go to the first one. So the answer, part A. So we have log a to the 7 plus 3 log a to the 2. So if you get a problem like that, the first thing is you have to have separate logs first. So that means since we have this number, what we're going to do, we're going to bring this in using the power out formula backward. So you can write this one as log a to the 7. We're going to bring 3 inside. That means it's going to be a power, which is log a 2 to the 3, because the 3 go as a power. Now we're going to simplify them inside first. So which is simply log a to the 7 plus log, we know that 2 to the 3 means 8. Now you can see this is a sum. Sum means we multiply the two numbers inside using the property number, property 3. So if you because since the sums you multiply the numbers inside, so which is log a, you multiply the two numbers, so 7 times 8, and then we have log a, 7 times 8 is 56. So that's what you get. Since you don't know a, you cannot simplify further than that. Good. So let's go to b. So which is 2/3 ln 8 minus ln 12. Again, we're gonna bring the powers inside first, because before that we can't do anything. So that's the first step. So if you bring the powers, so you can write this one as ln 8 into 2/3 minus ln 12. So we bring the powers. Now we're going to simplify that number first. So it's ln. We can simplify this one as 8. You can write this one as 1/3 square. So that is the best way to simplify this. We know that 8 1/3 means 2. So this is going to be now ln 2 squared minus ln 12. You can skip some of the steps, but I'm writing all these steps for clarity. So this is ln 4 minus ln 12. Now since this is a subtraction, this becomes a division. So this is going to be ln 4 divided by 12. That means ln 1/3, because 4 12 means 1/3. So this one you can write in expanded form. You can write this one as a subtraction again. So you can write this one as ln 1 minus ln 3. But we know that ln 1 is 0. That's going to go away. That means you're going to get your final answer as minus ln 3. So that is the final answer for this problem. So we use the property that ln 1 equals 0. Good. There's another way to simplify this one. So I'm going to simplify this here. So for example, when you have ln 1/3, you can write this one as ln 3 to the negative 1, because 1/3 means negative 1. Now we can bring this power out using the power out formula. So if you bring the power out, this is simply going to be negative ln 3. So that is the shortcut version of that. So you're going to write 1/3 as 3 to the negative 1, and then bring the negative 1 outside. So it's negative ln 3. Okay, so let's go to the next problem. C, so which is we have 3 log, that means base 10, plus 1/2 log x plus 1. First we're gonna write this one as, so we're gonna bring 3 inside as before, 3 and 1/2 inside. So if you bring them inside, you can write this one as log x to the cube plus log, so this is half power. So half power means square root. So you can write half power square root. Now what we can do, you can see these are just the sum of logs. So that means we're gonna multiply the two numbers, but half power is square root. So that means you can write this one as simply log. You can write say this is x cube and x plus 1 square root, but don't forget the bracket, because if you do not have bracket, it has a different meaning, because it means that you take the log of the first one and then multiply by the second one. So you need a bracket around or parenthesis around. Okay, so let's do the last one. So which says that 3 ln s plus 2 ln t minus 1/2 ln t squared minus 1. As before, we're going to bring all those powers inside. So we can write this one as ln s cube plus ln t squared, and then you can say this is minus ln t squared minus 1 to the half power. So I leave the negative sign here and then bring only the number. So now we have two additions and one subtraction. That means we can combine all three together. So you can write this one as natural log s3 multiplied by t squared and divide by, because of negative sign, t squared minus 1 square root. And in this case, you do not need a parenthesis because it's just one fraction. So you take the natural log of that. So in this case, you don't need a parenthesis. Okay, so that's how you write in the condensed form. So let's try to do some evaluation problems, like how to use these to simplify certain numbers. So we have the evaluate part A, log base 4 2 plus log base 4 32. Second one is log base 63 7 plus 2 log base 63 3, and then log base 280 minus log base 25, and then minus 2/3 log 8. Let's see how we can simplify certain all of these expressions. So the answers, so we're going to go with the first one. So what we're going to do is we're going to use the, because it has the same base, and then it's a sum formula. So that means we're going to multiply the numbers. So we have log 2 plus log 32. So it means it's the sum and the same base. It's the same base and the sum. So you can just multiply the two numbers. That means this can be log 4. You multiply the two numbers. So 2 times 32. So which is log, you can see 4. 2 times 30 means 64. And then we know just by the definition, because since 64 is 4 to the cube, this is simply going to be 3. The reason is we know that 64 equal 4 to the cube. The index is the log. That means it is 3. So the answer is 3. So you can see this simplifies to 3. It's interesting. B, so we have log 63 7 plus 2 log 63 3. The first thing we're going to do is we're going to bring this inside first, because you have to have separate sums. You cannot have any coefficients in front. So that means this can write as log 63 7 plus, if you bring it in, you can see this is log 63 3 squared. So 3 squared means 9. So you can write this one as log 63 7 plus log 63 9, and then you multiply the two numbers. So that means you can write this one as log 63 7 times 9. So it's 7 times 9. So that means this is log 63 63. So it's the same number. That means this has to be 1 using the property number 1. So we talk about when you have log AA, which is equals 1. The reason is how to write 63 as a power of 63. This, the power is 1. So it's 1. And then we have C. So C is easy because you can see this is log 280 minus log 2 to the 5th. This is a subtract problem. That means a division. So it is log 2 to the 80 over 5. 80 over 5 means 16. So you can write this one as log 2 to the 16. 16 means 2 to the 4th. This is 16. Since 16 is 2 to the 4th power, the answer is 4. The reason is 16 equal 2 to the 4. Good. Okay, so the last one is also very interesting. D, we have negative 2/3 ln 8. So what we can do is we can bring the power inside. So it is ln. So we can actually do this problem in two different ways. I'm going to bring the power inside method for this problem. So it is 8 negative 2/3. So you bring the power inside from the power out formula, and then we can simplify this. So ln, how to simplify this? You can write this one as 8 1 1/3 and then negative 2 power. 8 1/3 means 2, so this is ln 2 to the negative 2. So 2 to the negative means 1/4. So you can write this one as ln 1/4. So again, we simplify something like this earlier. So you can do this in two different ways. You can write this one as ln 1 minus ln 4, but we know that ln 1 is 0. That means this is simply negative ln 4. That is one way. The other one is 1/4 means 4 to the negative 1, so you bring the negative 1 out. So that's the second way to do it. Okay, so let's do another type of problem. So how about these? We can write them in expanded form. So write in expanded form. Write in expanded form. Expanded form. So the first one is, let's say, a log a x times x squared plus 1 square root. Again, you need a parenthesis around because otherwise it has a different meaning. Now what we can do is, this is a product, so you can write this as a sum. So it's a log ax plus log a x squared plus 1 square root means half power, so you can write it like that. The half power equals square root. We can bring it outside, so that means this can be log ax half power. Half power means you're going to take it out, so this is log a x squared plus 1. So the question is, can you simplify this further than that? You cannot, because we have x squared plus 1. There is no way to simplify x squared plus 1, because you can only simplify when you have a product. So you cannot simplify this further than that. That means that is the answer for that. That's the final expanded version of that. So let's do part B. How about this one? Let's say you have natural log x cube minus x minus 1 to the let's say 4th root, and then you don't need the parenthesis here, because when you have a fraction like that, you can just leave it like that. You don't need a parenthesis. Okay, so again, it's a division. So division means it's a subtract problem. So that means we can write this one as ln x cube, that's the first one, minus ln the other term. What's the other term? X. So other term is x minus 1 to the x minus 1 to the 1/4, because fourth root, so 1/4. Good. And then we can write the power out. So use the power out formula. So we're going to bring it outside. So that means this you can, and also you can bring 3 outside. So you can write this one as 3 ln x minus 1/4 ln x minus 1. And can you simplify this further than that? No, you cannot simplify this more than that, because there are no formulas for difference or sub addition. So there are no formulas for sum and difference. So that means that is the final answer for this problem. So let's do maybe one more, like little complicated one. So how about this one? So let's say we have a log any base a. Let's say x squared plus 1 square root divided by x3 x plus 1 to the 5th power. Again, you don't need parenthesis here, because this is one fraction, so you don't need that. When you have multiplication, then only you need that. Okay, good. So again, so you have multiplication and division. So whatever the multiplication become a positive one or addition one, the division one becomes subtraction one. That means you can write this one as a log a to the x squared plus 1 half power, that is the term on the top, and then minus from the bottom we have x3. That means it's a subtract problem. So this is a log a x cube, and then minus there's another one which is log a x plus 1 to the 5th power. Good. That's the first step. you write, you separate them. If it is in the numerator, it is a positive term. If it's the denominator, it is a negative term. The next step is bring all those powers in front. So that means you can write this one as 1/2 log a x squared plus 1. This term you cannot simplify further. Minus 3 times log ax and minus 5 times log a x plus 1. So you cannot simplify this further than that, so you have to leave the answer in that form. Okay, so let's talk about the property number 4. So property number 4 is what we normally call the change of base formula. So we are done with major results, so we have some few extra results that can be helpful. So this is what we call the property number 4. Property number 4, this is what we know, change of base formula. Change of base formula. So we have two bases. So we have A and we have C, two bases, and B, that's just a number. B positive numbers. Okay, so it's a positive real numbers. Then we have this interesting result. Then what happened? The log base A to B, you can write this one using any other base. So this simply equals to, if you use a general base C, some other base C, this simply equals to log, you take the log of B term divided by the log of A term. So what you can do, you can take the log of B and log of A, and you divide the two. So this log become a fraction or ratio. So be careful. Okay? And then we have some. So that's a general formula. So C can be any other base. So let's look at those common bases that we have. Let's say you're going to use C equal E, the natural log. So if you use the C equal E, the top become natural log B over natural log A. If you use base 10, you can write this one as log B over log A. And the interesting part, you can see that it doesn't matter what base you use, you're going to get the exact same answer. So if you use a calculator, so what we normally do, we use calculators to find this. So we use a calculator. So we normally go with the natural log one. But it doesn't really matter, but make sure that you write at least 3 decimal places when you write ln B and ln A. And then at the end, you can round it to 2 decimal places. So when you write this, you write 3 decimal places. When you round it at the end, you write 2 decimal places. Okay. Good. So let's look at how we can prove this result. Okay, you can also skip those proofs using the timestamp, but I'm just giving proofs in case you are interested in this one. So let's look at how to prove this. It's a very simple proof. So what we're gonna do, basically, we're gonna say this quantity is k. So the proof. So we're gonna let k equal the log a to b. Then you can just use the definition, okay? Because by the definition, this means that a to the k equal b, just by the definition of the log. Because this is a log a b equal k, that means a k equal b. Now what we're gonna do, the common practice, what we're gonna do, we're gonna take the log of both sides to the base c now. So we can take log c on both sides, because this is like a common trick that we use in the future. So take log c. Okay, so that is the one we did. So if you take log c of both sides, what will happen? So it is log the base c a to the k equal log base c b. So what we did, we take log of this expression on both sides. We have ak equal b. What we did, we take log of both sides of that expression ak. Now what will happen, we can take the power out formula, so we can take the power out, so we can write this one as k log ca equal log cb. Now what we can do, we can divide by this, so that means once you divide, you're gonna get k equal log cb over log ca. So that's exactly what we want to prove, because we know that the k is simply log ab. Okay, so that's a proof. It's a very short proof. So we use a special trick here, because this is what common trick. We take natural log. This is not the natural log. It's log c of both sides, because we have ak equal b. The expression just take the log. Okay, so and I have like a simple note here. So there's like some special simplification. For example, let's say taking c equal b. If you take c equal b, you can simplify the numerator. So if you take c equal b, what will happen? Log a to the b by this simply becomes, if you take c equal b, the numerator have log bb over log a like ba, because you take c equal b, so it becomes ba. But we know that log bb equals 1. That means this simply becomes 1 over log ba. So what this says, so we change the order like ab to ba, it can be 1 over. So that is a interesting result. So it simply can be proved using the base change formula. Log ab equal 1 over log ba. Okay, let's look at some examples now. So we have these problems. So let's look at approximate log base 2 to 3. So if you get something like that, what you can do is you can use the base change formula. So I'm going to use the base e. You can use any base. So if you use the base e, you can write this one as ln 3 over ln 2. That's what the formula says. So that means if you use a calculator, you end up getting 1.099, and log 2 is 0.693, and if you divide these two, you end up getting 1.586. Let's say what happens if you use base 10. If you use base 10, this equals log 3 over log 2, and if you use a calculator, you're going to end up getting log 3 is 0.477 and log 2 is 0.301, and again if you divide these two, you end up getting 1.585. So you can see that this is very close. If you have more decimal places, it will be more accurate to but in theoretically it doesn't matter what base you use, you're gonna get the same answer. But since we have approximations, you want to make sure you write enough decimal places, then it's going to be very clear, and you can see that they are very close. Okay, it should be exactly the equal, but since we ignore some decimal points, we did not get the exact answer in this case. So let's do one more problem. So theory is over, so we just doing more examples. How about this one? Let's say you have log square root 2 base to square root 5 number. Again, we can use the one of the bases. Let's use ln. So if you use ln, this can be ln square root 5, that's the numerator, divided by ln square root 2. Now square root means 1/2, so you can write this as 1/2 ln 5 divided by 1/2 ln 2, and you can see 1/2 and 1/2 get cancelled, so that means you end up getting ln 5 over ln 2. That is the exact value. Or you can see, even if you use log, you get like log base 10, you get log 5 over log 2. That's what happened, because again 1/2 get cancelled. So if you use any of those forms and then if you use a calculator, you will end up getting 2.322, like something like that. So it's going to be very close to 2.322 using any of those forms. Good. So let's look at maybe one graph and how to graph these some of these functions, just one of them, just to see how we can use these results. So let's look at this problem. So let's say graph y equal a log 1/2 base x squared or something like that. Because we cannot do this earlier. We don't know how to do x squared. But what we can do, we can use some of the algebra. So the answer is, so we have y equal log 1/2 base x squared. Now what we can do, we can use one of those logs. So let's use the base change formula with ln. That means this can be ln x squared divided by ln 1/2. We can write it like that. And then from the top, you can bring 2 out. So that means you can write this one as 2 ln x. And the bottom 1/2 you can flip over, that means 2 to the negative 1. So that means you can write this one as negative ln 2. So that means if you write this as a coefficient, you can write this as a negative 2 over ln 2 and then ln x. So you can see this is just a coefficient. And what can I say about this one? ln 2 is a fraction, positive fraction, because ln 1 is 0, ln e is 1, so it's between 0 and 1. And then we have negative 2, so that means this number is it's like negative 4 or negative 3, something like that. So what's going to happen is just the natural log function, you're going to flip over and scale by this number. Flip over and scale. So that means your graph going to look like this. So we can start with y equal ln x. So which is the simple graph. Going to go like that, pass through 1. So what we can do now is you can flip over and scale. So that's what happened. So that means the final graph is minus 2 ln 2. ln x is simply flip over and scale. So flip over and scale. So that means it's going to be very similar. So it's going to again goes through 1. So it's going to be again like that. So it's a flip over and scale. So most of the changes you can see here. Okay. So it's going to be flip over and scale. So the original graph is like this. So that's the original graph. So scale it and flip over. Okay. Okay. So also we have some other results that are useful in the future when you try to solve certain problems. So I'm going to write this as the last property. This is property number 5. Property number 5. So we know that so since let's write since y equal a log a x is a one-to-one function. It's a one-to-one function. One-to-one function means we know that if there's a one-to-one function, something interesting happen. As that means if you give one y value, there's a one x value. That's the one-to-one means. So that we can use to solve problems. So the first result is, this is like a basic result. It's not because of one-to-one. The first result is if x equal y, then the log of those two should be the same. So this is a kind of major property that we use later to solve certain problems. So if you have two algebraic expressions, actually we already used that in the previous problem. when you have two algebraic equations, if you take the log, this will be the same if the numbers are in the denominator. So that's like one thing. And then the second one is coming from the one-to-one. So this coming from the one-to-one implies that if the log are the same, so for example log ax equal log ay, this implies that x equal y. So this is very useful. This is a one-to-one property. So you can see more problems when we solve log and exponential equations later in another section. We can use this property number 5. It's a very important property, especially part 2. Part 1, like part A, we already used in a previous problem. When you start with some algebraic expression, you can just take the log of the two sides. Good. So we can say these are used in solving exponential and logarithmic equations. So we can have a note. These are used in solving exponential and log equations. So let's try to do one problem just to see how we can do it, but we can do more problems in a different section, in a different video. So let's just do one example to see how we can use these ideas in a problem. So let's say solve for t the equation 3 equal 5 to the negative t minus 1, something like that. Especially when you have different numbers, different bases, we're going to use log. So that's what you dream if you have different bases. So what we're going to do, we're going to see like a common trick, what they call the take ln. It is a natural log. Take ln of both sides. We take the natural log of both sides. So if we take the natural log of both sides, so we have 3 equal 5 minus t minus 1. That's what we have. If we take the natural log of both sides, so that means we can write this one as ln 3 on this side, other side ln 5 into 3 minus 1. Now ln 3 we have to leave it like that. So what can happen here is you can take this power out. This is the power out formula. You can take out with negative t minus 1 ln 5. So ln 3 and ln 5 are numbers. And if you simplify this a little further, you can write this one as so this is going to be t 1 minus t. So you can write this one as 1 minus t, and then ln 5. Now what we're going to do, we're going to divide both sides by ln 5. So you can write this one as 1 minus t equal ln 3 minus L over ln 5. So you divide by ln 5 both sides. Now we can isolate, you can subtract 1 from both sides. So you're going to solve for t. That's what you're trying to do. So this is very easy to do. So you're going to subtract 1 from both sides. So we have negative t equal ln 3 over ln 5 minus 1. When you multiply by negative from both sides, you just change the sign of everything. If you change the sign of all of them, so t is going to be 1 minus ln 3 over ln 5. We don't need this many steps, you can just write it, but I'm just writing all these steps. And then what you can do is you can just use a calculator to find this. So this is roughly, if you find ln 3 and ln 5 and divide, you should end up getting 0.317 as the answer. This is how you can use the log methods to solve certain exponential functions. And you can see that we use the natural log in this case. Even you can also use log, you still get the same answer. Taking natural log is very common. So this is how you solve, how you use log properties of logarithms to solve certain exponential functions. But we have a separate video that basically there are two separate videos. One for the solving exponential functions, and there's another video to solve logarithmic equations. So you can look at those videos after you understand what we discussed in this one. Okay, so let's have a summary of what we did so far. So as the first result, we have log a1 equals 0 and then log a equals 1. And as a special case, we have log ln1 equals 0 and ln e equals 1. And then the second one, we had as a property number 2, a log ax equal x and log ax equal x. Again, as a special case, when a equals e, we have e ln x equal x and ln ex equal x. So this property for the first one, we know that this is true for x greater than 0, and this one is true for any real x. Um, the same thing here, so this is true for x positive and this is true for any x. Good. And then the property number 3, so as a like a special case, we can have a, for example, replacing x by ax, we have this special result. This is also very useful when you solve problems. So this happen when if you replace x by ax. So and then use the power out formula here. And then you're going to end up with this special result. So then we can have a property number 3. So this is a major result of logarithms. Log log of a product equal sum of logs, and then log of a quotient equals difference of logs, and then log a to the r equal r log a. This is what we normally call the power out formula. And then this is true for any base. So this is true for any base a which is positive and not equal to 1. Then we have property number 4, which is what we normally call the base change formula, which is log AB equal, if you use the natural log, this is equals to, you take the natural log of B first divided by natural log of A. So you can use any base. If you use base E, it is ln B over ln A. If you use base 10 or the common logarithm, you have log B over log A. It doesn't matter which formula, you get the same answer in both cases. And finally, we have property number 5, which is useful when you try to solve certain problems. So what it says that if x equal y, you can take the log of both sides. So in practice, what we normally call this property is take ln of both sides. So that's exactly what we do in certain problems, take ln of both sides. That's the first result. And the second one is if we have the same log, it says that the numbers has to be the same. So x has to be equals to y. And this is due to the one-to-one property. And then, so those are the 5 properties that we discussed. And there are certain cases where we students make mistakes. And let's talk about them quickly. So for example, so these results are not true. So what the first one says, log a m plus n, you cannot simplify this further than that. So it doesn't equal log m plus log a n. What we have is the product equals the sum. Similarly, if you have a difference, you cannot simplify this further than that. What we have is log the quotient equal log am minus log n. And then also log, if you have a quotient, it doesn't equal to the quotient of logs. What we have is the base change formula. So if you have two numbers mn, what you can do is you can pick any base a, you can write this as log am to log an. So that is the warning, because you have to make sure that you understand these, because none of them are true when you solve problems. So this is the end of logarithmic discussions, and we have the solving exponential and logarithmic equations. We can discuss that in 2 separate videos.